Well, it looks like it's time. Welcome back, everyone, and happy Thursday. It's almost the weekend. I think we mentioned this last time, but noteworthy thing about this class meeting is after we conclude class today, we're 25% done with the entire semester. So 6 more weeks to go. Well, bigger announcement is, of course, that the first exam is going to be Monday of next week. That's the official date for the exam, like we mentioned. That'll be the day we don't have class. So it's the ideal time to schedule your exam if you can make it work on Monday. But if there's any issues that occur, don't hesitate to email or write a message in Canvas. But you're also welcome to schedule the exam, like we mentioned, between Monday the 29th up to Thursday, July the 2nd, just to make sure things work out with your schedule and with the testing center schedule as well. But any questions or comments whatsoever, folks, about exam one? Okay, again, the exam is going to be scheduled in the testing center that you selected. So if you haven't seen the instructions through Canvas on how to schedule, don't hesitate to reach out. I'll be happy to get you set up and ready to go for scheduling your exam. But aside from that, here's what we were looking into last time. Last class, we were dealing with the derivatives of polynomial and exponential functions. And this is the list of derivatives we studied quite intensely on last class meeting. The constant rule, the power rule, derivative of an exponential function, that's a bit of a tongue twister, when it's a base C exponential, and the general derivative of any exponential function was just a selection of some of the properties we looked at. Then we took a peek into what's going on with the product rule and the quotient rule, and so that's where we're going to begin today. So here's where we left off on last class. We looked into the definition of the product rule. Here's how it's defined if we're using Leibniz prime notation. Newton's prime notation. If we're using Leibniz notation, the derivative of f of x times g of x is indicated this way. We copy f of x, then we calculate the derivative of g of x, then we copy g of x and take the derivative of f of x. Seems kind of weird and almost backwards in a certain sense, because when I wrote it in Newton's prime notation, I specifically chose this order for reasons we'll see later on with the quotient rule. But whether you did the derivative of f first and multiplied by g of x, or did the derivative of g first and multiplied by f of x, it will still be the same exact result because you can switch the order across addition. So as long as you copy one function down, differentiate the other, then copy the opposite function down and differentiate the other, like when we did on y equals x e to the x, you're using the product rule correctly. So we showed how the product rule goes for a situation where it's absolutely required. And then the last comment of the day was pretty much watch out for functions like these, where you can use a product rule, but it's just highly discouraged. And I think the one thing I missed last class was I needed to highlight and put a y prime there. So if you forgot to put a y prime, as I think I did as well the last part of class, don't forget the prime to say we took the derivative. It just happens to be the same as the original function. So our goal is to practice more with the product rule, take a look into how the quotient rule goes. But any questions whatsoever with the refresher? Okay, well, let's practice some more examples to see how all this goes. Here it just says bluntly compute the derivative, or it could just say differentiate. They look somewhat similar to what we were doing in the last section notes. And in fact, if we put in a plus right in the middle there, that's just like the very last section. It can be differentiated really fast. But when we bring it back to the original real function, it's not the same story any longer. For this, we must use the product rule to compute it because we have a bona fide function, that's not a constant, x cubed, multiplied another function that varies with the variable x, e to the x. And so for this, we must use the product rule. And when you're starting to study the product rule to get a feel for how it goes, this is a way sometimes it's helpful to memorize it. F prime of x is going to take a derivative of something, copy something down, add to it, copy something else down, and take the derivative of something else. So there'll be a derivative that goes in right here, a derivative that goes in right here, and the last placeholders we're just copying down the function. So this is really just the product rule. It's in kind of a placeholder format when we write it out this way. And if you like this approach, the one thing it allows us to do is go back up to the original function, split the factors, x cubed e to the x, and just drop them in the placeholders in the same order. So x cubed e to the x cubed e to the x. So where the highlighting is, that's just reminding us to differentiate. Don't forget to put in the prime symbol or the d by dx symbol to remind yourself you're differentiating at that step. And then from here on out, just two derivatives to go and our work is done. So that's the first step. Just write down the schematic, the 4-match-4 product rule using placeholders. On the next step, take those derivatives and our work is complete. But here it's not so bad. This is just the power rule. To differentiate x cubed, 3 comes down. New power of x is just 1 reduced, power 2. So that's this rule right here. The power rule general version applied in this way, whether it's x power 30 or x power 3, it's always the same pattern. Exponent becomes a coefficient, and the new exponent drops by 1 each and every time. Then we go to e to the x. This was just meant to be copied, so there it is. X cubed is copied as well, so keep on copying. Now, when we differentiate e to the x, let me see if I can bring, no, that'd be too much to bring back. When we go to differentiate e to the x, I think we said before, it's kind of like the world's nicest derivative in a certain sense. Let's scroll down to see both of them at once. If it's e to the x, the derivative is done just by putting in e to the x. If it's, say, a to the x, where a is 7, 12, a third, anything like that, not base e exponent, or excuse me, the base e number, then you just have to multiply it by the natural log of a. So this one's nice. Derivative of e to the x is just itself. Once we put down e to the x, our work is 100% done right at that step, which is kind of nice in a way. We just had to know the product rule would come up. The derivative of this function is not the derivative of x cubed times the derivative of e to the x. It comes with two terms altogether. So when we use a product rule, this is the result we're expecting. Well, any questions at all, folks, on the completion of this one? Okay, well, that was so fun. We'll just do it all over again with the new function, g of x. Here we have a power function, another power function, so a combination of those. The power is negative, but that's okay. The problem can be differentiated right here using the power rule, whether it's a negative exponent, whether the exponent is pi, an irrational number even, it's always the same pattern. And now we have a base 2 exponential, 2 to the power of x. One thought you might have is you could distribute 2 to the x into the group, but that just means you'd have to use the power rule twice. It's not going to simplify the problem at all. It actually would make it a little bit more convoluted. In this factored form, this is probably the best way to use the product rule. We can think of that entire piece right there, that factor, as being the first function, that factor as being the second function, and if you want to just write down the derivative and skip to this line right here without placeholders, that would be completely appropriate. But while we're learning it, we'll take the extra time to just write down the product rule in this format. G prime at x through the product rule becomes the derivative of something, copy something, then don't forget plus in the middle, then copy, take the derivative again. In this first placeholder, That's where the derivative occurs, and the very last placeholder, a derivative will occur. Then it's the same strategy as before. Just copy the functions, dropping them these placeholders, maintaining the same exact order. So 3x power negative 4 plus 5x cubed, 2 power of x, 3x power negative 4 plus 5x cubed, 2 to the power of x. And now it's all set up. It's not done, but we're done using the product rule. All we're going to now do is finalize this derivative. This is one we saw in the prior section. And same with this one. These are two derivatives that we're ready to go with. Any questions whatsoever with just the initial setup? Okay, let's try it out again. Or rather, let's complete the problem is the better word to say there. The derivative of g at x is going to be, now take this derivative here, we're going to still need parentheses to make this algebraically correct. Power rule says it's negative 4 times 3, so negative 12. The new exponent drops by 1, so now it's a negative 5. Then through the sum rule, rinse and repeat. 5 is going to get multiplied by the exponent 3 for 15. New exponent is 1 less, so now power 2. And that derivative is now complete. That now we just start to copy 2 to the x plus 3x power negative 4 plus 5x power 3. And then last step, we differentiate here. Here we need to be a little bit careful when we do this derivative. It's going to come out as an exponential 2 to the x, similar to what we did with the e to the x when we differentiate that exponential function. But if it's a base 2, there's more to the story. We have to multiply by the natural log of 2 to finish it off. So that's this part right here, natural log a, that finishes off that full derivative. So we used that formula there, where a is playing the role of 2 in our current problem. At this stage, we're done. We could possibly distribute 2 to the x in, or maybe factor out 2 to the x. But even if we factored out 2 to the x, there's going to be no like terms here. All the powers are completely different. So I'd say this is a pretty good stopping point on this problem. So that's the power rule, and the product rule in a nutshell. Whenever functions are being multiplied like this and we cannot simplify them, this is the rule we must use. Next, we're going to turn this around and take a look at what's going on with quotient rule when functions are being divided and we can't simplify. But any questions or comments at the moment? Okay, so let's take a peek at the next big rule, the so-called quotient rule. So again, we have it in Newton's prime notation, and then down below in Leibniz notation as well. I'll typically do it in prime notation whenever I'm writing down the quotient rule. And here's what the format looks like. If we differentiate a bona fide quotient of functions, and it's assuming we cannot simplify these, and both functions are non-constant. Then the way this combines is we take the derivative of f of x, multiply by g of x, then subtract. Watch for that sign switch. For quotient rule, think a minus occurs. Copy of f of x and multiply by the derivative of g of the x, and then divide by g of x squared. So that's the entire format of the quotient rule. It's a little bit more built up this time. A squared occurs in the denominator for the g of x function. But it's sometimes very beneficial to view this in view of how the product rule goes. The product rule said if it's f of x times g of x, then the result is f prime of x times g of x plus f of x times g prime at x. So let me quickly color code these the way we had before. So even though these rules, they kind of look random at the first when you first look at them, if you compare how it changes going from the product rule down to the quotient rule, that really helps the brain kind of internalize this and see the patterns. Notice that in the quotient rule, the numerator is almost completely identical to this rule here, the product rule, except for the sign flip, highlighted in yellow there. So watch out for the sign flip. If it's a product, you have to use plus, and that's a great way to memorize it. Think P for plus, P for product rule, and then you're on the right, what was the word I was going for? You're on the right step there, I guess is what I was trying to say. Had a blank there. If it's a quotient rule, then use the minus and you're in good shape. And the next new thing about the quotient rule is you divide by the function in the bottom squared. So that's a rule. We'll practice it down below this little border here just to illustrate how it goes. Any questions or thoughts with the quotient rule at the moment? Okay, and I thought kind of a fun one to illustrate the power of this quotient rule would be back in section 2.8, where we took some painstaking effort when we did this section 2.8 to this week to differentiate x squared minus 1 divided by x plus 3 using the definition of the derivative, which meant we were using the limit as h goes to 0 of that difference quotient, g at x plus h minus g of x divided by h. So that was the definition of the derivative there. And it's a lot of work. It looks like I forgot to even copy down the plus h if I recall correctly. So thanks again for the student for spotting that error there. Easy to make a mistake when there's this much stuff. So let's try it out again. Now that we have a fancy new formula, let's just see how fast this can really go. So I'm going to copy down the same function, x squared minus 1, x plus 3. By the way, when you're doing math problems, this is the easiest mistake to make ever. If you were copying problems on a different piece of paper, just double check you didn't change anything about the problem. Okay, I think we've got it down. So now if we're differentiating that function, it's a little bit annoying because it's called g of x, and g of x is also in the definition of the quotient rule. But you know, it's really okay because it's less about the name of the functions, and it's more about how the pattern is when you put it all together. So in identifying that pattern, we think of the top function and the bottom function for the quotient rule, or the numerator function, denominator function, just takes more time to say it that way. Then when we go to differentiate g prime at x, the thought is you can just put down essentially 5 different placeholders for where the functions go. So just mimicking and mirroring how we did product rule, let's write this down to set it up. We'll take the derivative of something, copy something else. Remember it's a quotient, so a minus will go inside there. That's easy to forget. Then go copy and differentiate. And in the denominator, we square something. So there's only 2 derivatives that occur in this spot and in this spot. When we go to fill it in, we're just going to put in the functions in the order, top functions and bottom functions, going left to right. So start off putting in x squared minus 1, then x plus 3, copy that again at the last placeholders, x squared minus 1, x plus 3, and then in the denominator, that's always the function that came from the denominator. And that's a great way to think about it. If the function g is in the denominator, then it will go still in the denominator, but now to a power 2. So that means pull x plus 3, drop it down below. In our placeholder structure, we already had power 2, so now it's set up. So it looks like a lot of stuff, but remember, this problem had a lot of stuff too, so it's a good trade-off to deal with just this. We need to differentiate and then simplify and see where this is heading towards. But any questions at the moment with where we're at now? Okay, so next, let's differentiate. G prime at x equals. First, the derivative of this one, this will become a 2x. The derivative of -1 is a constant, so it goes to 0. That means we only have only one term, so we don't need parentheses. We just multiply that by x plus 3. We subtract x squared minus 1. And now multiply by this derivative. This derivative is kind of nice in a way. The derivative of x is 1. The derivative of 3 is 0. So the whole derivative of this is just a 1. That means all the derivatives have been resolved. The whole thing is divided by x plus 3 squared. And now we can simplify from here on out. We still have to simplify all of our answers, but that's just going to involve distribute 2x inside. That'll give us a 2x squared plus 6x. Distribute the -1 inside this group to get minus x squared plus 1 over x plus 3 squared. Now we have like terms, so we take x plus 3 squared, and altogether this is just one copy of x squared plus 6x minus 1. So really the major work on this problem was just write down the format for the quotient rule that we took in this step, differentiate, and just simplify from there out. Checking with how we did it last time, let's pull this up once again. We got to the same place, but it was a different kind of adventure taking this limit. But it is kind of satisfying to see how our new machinery here, properties of derivatives, differentiation rules and such, can simplify the definition of the derivative into something that still involves some work, but not an explosion of algebra like in that prior problem. Well, that's the introduction, a typical example for quotient rule. Any questions at the moment with this one? Okay, when we introduced the product rule, we really did two introductory examples. One example where the product rule was required. So likewise, for this one, quotient rule is required. But keep in mind, that's not always a firm requirement. Really, the whole reason the quotient rule is required is because the denominator involves two terms altogether. If we did something like what we did in section 3.1 along these lines, say 3x squared minus 6x plus 7 divided by the square root of x, you can use the quotient rule on that. But there's only one term in that denominator, and so it was easy to just divide all the terms by it, reduce them down, and then differentiate the result. I think this approach would be faster. But here's another one where quotient rule should not be used. So that's kind of a weird statement to make. We have a brand new rule. And the reason this is so important is you don't want to get bogged down in using the product rule and the quotient rule on problems where it's just not needed. You don't want to take the biggest sledgehammer to do a problem that requires a screwdriver, in other words. And this is one of those kind of problems. Y equals 1 over x to the power 7. Here, you can use the quotient rule. You absolutely will get the correct result. But you can do some algebra on this thing. If you just rewrite this as x to the power of -7, then all you're really using is the power rule to differentiate this thing. You can now say y prime is -7 coming down as a coefficient. Exponent is 1 less, so -8. You can leave it in that form, or you can drop this into a denominator. I write as -7 x power +8. Either form is completely acceptable. But this would be the whole resolution. And if you wrote down the quotient rule for this, you're going to get the same exact result, but there's no reason to work so hard in getting there when it's just a couple algebra steps and a really fast differentiation rule. So what we'll do next is just practice more with the quotient rule. But any last thoughts or questions about how this rule works? Okay, well, coming up next is a couple of typical examples where, again, the quotient rule is required. There's no way to do some clever algebra like we did in section 3.1, reducing that because there's one term in the denominator, or nothing like this form where it was really never a quotient rule to begin with. It's just a power function in a different form. But these, there's no sneaking away from these. We have to use the quotient rule in both cases. We'll save h of x for the very bottom here. So we can, once again, organize just like we did before. You notice you can't simplify these functions any further, but unlike that last example, the numerator isn't a constant. It's a bona fide function of x. Same with the denominator. It means you can't do anything like this sort of work to fix this. And even if you change things around, bring e to the x up into the numerator, you're just changing out from the quotient rule into the product rule. In fact, that would require even more rules, the chain rule, when you're dealing with e power negative x. So it's probably best to just differentiate it right in this format. We're organized by splitting into two functions, the top function versus the bottom function. Then the derivative dy dx through the quotient rule takes on this form using placeholders like before. Differentiate, copy, then don't do as I did. Let me control Z that out. Minus in the quotient rule. That's just weird muscle memory, I guess, to put in a plus there. Copy another function, differentiate, and then raise the denominator to power 2. So 2 derivatives to take, but 5 placeholders to fill in. Yet it's all about the pattern, really, like we mentioned before. Go top function to bottom function, plugging them in left to right to get the numerator. So it's x, e to the x, e to the x, and take the denominator, plug it into the denominator, squared, so e to the x goes here. And now we're just taking our 2 derivatives and simplifying. So here's the setup. There's really not too many more steps to take here other than simplifying as well. But any questions to this stage? Okay, well, we're nearly there. Going left to right, this is a nice derivative. Derivative of just a variable x is always a 1. So we throw in a 1, and that one's done. Multiplies e to the x minus x. The next derivative to take is the derivative of e to the x, but that's the other nice one. Derivative of e to the x is itself, so it just goes down below. Here, this is a new exponent property we haven't put down on paper yet. So just for the sake of the algebra review, if you have a to the power n to raise to the power of m, in this configuration, I think it's the first time it's occurred in this class, this becomes a to the power n times m. So e to the x to power 2 just means x and 2 multiply as exponents, and this becomes e to the power 2x. And it actually simplifies from here on out, so let's keep on going. We definitely want to simplify 1 times e to the x. That's not a good form to leave it in. You want to just write it in as e to the x itself. So dy dx is now e to the x minus x e to the x over e to the x, excuse me, e to the 2x is a better way to say that. There's e to the x's everywhere, so that means it reduces. We can factor out an e to the x, leaving behind 1 minus x. And e to the 2x, we can leave it in that form, but algebraically, we could also write it as e to the x times e to the x, which makes it just a little bit nicer on the eyes for cancellation. This e to the x cancels with that copy of e to the x. And now we can see that the result for this derivative is 1 minus x divided by e to the power x. So that's the whole story to the derivative. Actually, the algebra, simplifying it down, looks like it took more work than the calculus, finalizing all the derivatives to this step here. But we did it, folks. That's a second run through the quotient rule. We're going to try it again with the function down below. But any questions so far getting through any of these? Okay, well, let's try this out again. And then we'll look into the next topic in these notes, which is more just kind of summarizing and wrapping up all the methods. This one, h of x, it's absolutely the quotient rule, but notice it has quite a bit going on. The numerator has two terms, the denominator has two factors, so there's lots to do on this one. But fundamentally, the first thing that's going on with this one is it's a quotient rule. So first, we're going to use quotient rule to get started. Let's set that up as we've done before. There is a numerator function, denominator function. So the format is going to look like this. Derivative and then copy, subtract, copy and then derivative, multiplying those two groups together. So two terms in the numerator, and then a denominator squared. So that's our schematic. Once again, for the quotient rule, let's put in some highlighting just for emphasis on the derivative portions now. Then carefully copy in our results of what the top function and bottom function are. X squared plus e to the x squared times e to the x squared plus e to the x squared times e to the x. And then finally, what goes here in the denominator, the hint is just take the denominator function, x squared e to the x. So that's our setup so far. And, it's not too bad at the moment when we look at it, but you might have spotted another red flag with this. The idea here is essentially every time we discuss a brand new differentiation rule, they don't exist in isolation. They connect with each other. You can write down a problem that uses every single differentiation rule that we'll discuss in this entire course. It's probably going to be kind of a scary function, but it's very, very possible and plausible. And now when you look at this one, there's differentiation rules here for sure, but nothing too major. But this one is a bigger deal. X squared times e to the x. When we go to differentiate that one is a product rule. And we must use the product rule right there to get the right result. So the problem gets bigger than expected out of nowhere. And so this is a good idea to kind of split the problem up into chunks. We'll use the method of divide and conquer. We're going to resolve this product rule right here, simplify the result, and then plug it back in to the original derivative, h prime at x. But let's take a breather first before we launch into the product rule portion of this one. Any questions to this stage? Okay, let me copy it in as a new function we're going to pause and work on, y equals x squared e to the x. Because we know it's a product rule, two functions being multiplied, we can't simplify to eliminate the fact we have a multiplication of functions. We'll start by saying y prime equals, put in the whole placeholder structure, put in a plus in the middle because it's a product rule. I have two derivatives indicated. I'm running out of colors to color code it, so I'm just going to keep this all in green to remind me it plugs back here into that green result there. So take the factors, x squared, e to the x, and copy them as so in the first two placeholders, then again in the last two, x squared, e to the x. Then keep on simplifying. Y prime is going to be that derivative, which is a 2x, copy e to the x, multiplying it, plus x squared. Finally, that derivative is just e to the x. So that's the entire simplified result. It's going to plug back inside here. It'll still need parentheses. Doesn't hurt to put them on right now, just as a reminder for ourselves. But now we're unpausing the original derivative, h prime at x. We'll differentiate that as normal, and then just plug in our result here. Doing this as a whole separate problem just prevented us from having to copy a huge fraction line by line by line as we worked out the product rule, and it made the algebra just a little bit more controlled and easy to eyeball to spot any mistakes that might occur. So let's go back to the original. H prime at x is now going to be equal to, take the derivative here, that's going to be 2x plus e to the x. So this one came in a little bit nicer, only because if there's a plus, we're just using the sum rule. We differentiate each term. It multiplies against x squared e to the x. Minus, we'll need parentheses to stay on this one, x squared plus e to the x. Times the result of this derivative. We have it down here. Don't forget the parentheses, 2x times e to the x plus x squared e to the x, all divided by x squared e to the x squared. And finally, this is where the calculus ends, right at this step. Before we go on to the next stages, simplifying the function, any questions at the moment? Okay, and let's reiterate the reminder that we had back when we were in section 2.8. Sometimes the problems just get a little bit longer. Sometimes the algebra kind of explodes on us, and it's just part of a life. In a mathematics class, an engineering class, a chemistry class using calculus, these things happen, so it's good for us to practice these. Sometimes the results look like this in the homework as well, so we're supporting them by doing harder ones in the lecture notes as well. And it's kind of like what was going on here. This one was with the definition of the derivative. This was a lot of algebra. But this is a good bit on its own. And this is well worth the practice because when we are in chapter 4, this is what we're going to be doing. We're going to be setting it to 0 and solving when we're trying to optimize something. And the best way to solve that equation is to make sure you've simplified the thing on the left as much as feasibly possible. So that's why for these problems, let's put down here just a remark, we must simplify. It's the best practice and it'll be useful later on. So new line, h prime of x. This one actually simplifies a lot when we start distributing things through. We're going to use the distributive law, multiply here to here. That's going to be equal to 2x cubed e to the x. Then multiply here to here. That's going to be plus x squared. E to the x times e to the x is just e to the power 2x. So first part's done. I have the minus. I'm going to carry one overall parenthesis. And now our next step is FOIL this out. Take x squared times 2x e to the x. That'll be 2x cubed e to the x. Then finally, well, not finally, halfway there. Next, x squared times x squared e to the x is plus x power 4 e to the x. Now distribute with e to the x. When e to the x multiplies e to the x, it just becomes e to the x times e to the x, or e to the 2x is a better way to say that. So this is plus 2x. E to the power 2x is a more simplified way to write that down. And then e to the x times x squared e to the x gives us plus x squared e to the 2x. So here's the algebra just kind of exploding on us, but it's going to reduce a lot, so that's satisfying. And as far as that power 2 goes, we can raise each of the bases to that power 2. X squared would give us x power 4. E to the x squared would be e to the 2x. But it's not a whole lot of value in doing that. I would say either way you wrote it, it's just as good. This might be slightly faster to write. potentially. So next step, I'm going to copy to this point here, then distribute the negative sign. We have so far 2x cubed e to the x plus x squared e to the power 2x. Now here's the distribution step. Minus 2x cubed e to the x minus x power 4 e to the x minus 2x e to the 2x minus x squared e to the 2x. Okay, so that's the distribution of the negative sign, all of which is divided by x power 4 e to the 2x. And then we just keep on going from here. Let me see if I can manufacture some additional space. I'm running out of space on this one. You know, maybe this one deserves just its whole new page. Let's promote it down to a new one. Okay, now we're ready to finalize this. Just want to see if I can get everything on just one window here. There we go. When we go to cancel, we have, let's see, let's go carefully with the like terms. We have 2x cubed e to the x, and its opposite is there. We have x squared e to the 2x, and its opposite is also here at the very far right. So that leaves just two terms in the middle, x power 4 e to the x minus 2x e to the 2x. You know, now that we look at that, this does reduce even further. They're non-like terms, but if we factor out the greatest common factor from these two, we can cancel with what we have down the denominator. It looks like actually squaring these out was a good call after all, because now we can reduce further. And again, this is useful when we're in chapter 4. We need to reduce as much as possible to make the next steps on optimization go smoothly. And so this isn't for nothing. We're going to do these kind of things later on in that chapter. So let's keep on going further. This is a good review on algebra at this point. We can factor out a greatest common factor. I'll take out a negative sign as well. Negative x times e to the x would be the greatest common factor. That means we'll divide x here, leaving x cubed. The sign will flip to positive. E to the x cancels, and so just x cubed on the first term inside. And factor out a negative x e to the x. I'll flip it to positive 2. X cancels. And when you divide e to the power of 2x by e to the x, you just get e to the x. And all down below is x power 4, e to the power 2x. But we did before, as we did before, we can rewrite e to the power of 2x as e to the x times e to the x using properties of exponents. Then we get a new cancellation. The e to the x's cancel. The x will cancel with x power 4, making x cubed on the right. And so here's the whole result fully simplified. X cubed plus 2 e to the x divide by, oh, hang on, I messed that up. Nope, that's right. I'm canceling this x into that x, leaving x cubed e to the x. So we got it. This is the whole result of the quotient rule. It had lots going on because it wasn't just the quotient rule, it was also the product rule at the same time. And one thing I want to mention, as far as exams go, if this was an exam 2 question, I wouldn't put in a problem this convoluted on a real exam. Still, there could be problems we have to simplify in a real exam setting. But if you make it to this step right here, that's the step where the calculus really ends. And so when I grade on partial credit, even if you made a mistake on the algebra, you might lose 1 point maximum out of, say, a 5 or 6 point problem. So I'm going to emphasize the calculus more than anything, but practicing and brushing up on our algebra, seeing how these steps go, is important to us later on. But we made it through it, folks. I think this is the roughest question of the section 3.2 notes, probably the hardest question of chapter 3 so far. Any last thoughts or questions getting through this one? Okay, well, this is the part of the notes where we're just going to start kind of summarizing where we're at so far, wrap up this section. On the next table, here's the roundup of essentially all the major differentiation formulas that we have so far. We have that the derivative of the constant goes to 0. The good old power rule, we've already used that probably well over 20, 30 times. I've lost track for sure, but we use that a lot. Here's the nice derivative of a base e exponential. If you want to fill this out a little bit more, there's some stuff missing, I've noticed. There's also d by dx of a to the x is a to the x times natural log a. So that one is missing for no apparent reason. I think I copied this table directly out of the textbook and just did as the author did. I omitted that part there. There's the constant multiple rule, the sum rule, the difference rule. Notice that we're just writing f rather than f of x. So we're emphasizing just the name of the function, not the f of x and the g of x. It's just a way to paraphrase how each of these rules go. So the paraphrase for the product rule is that if you have two functions, f and g, and you differentiate, you do f prime times g plus f times g prime. Likewise, here's the quotient rule, the one that we just finalized, and the derivatives would go in those analogous spots. But don't forget to divide by g squared and the fact that the signs are opposite. So everything above, these two rows are what we did in the last section, and these are the two new rules we're studying in this section here. So that's kind of a nice roundup of formulas. When we start talking a little bit more about exam 2, this might be a good table to put down on your second exam, and probably including that omitted one here where the red dot is, to just get a feel, another look, another take at the product rule and quotient rule. Here's another interesting kind of problem where we don't actually know the functions. We just know that f and g, they must be differentiable because we're told to find the following values. And we have function outputs. So we want to do the derivative of f over g at 3. So we're going to get a numerical value this time. And likewise, f times g prime at 3. I think there's a problem similar to this one in the homework as well. So we're doing this also to support the homework, but mainly just to give another take on how both these new formulas go. So this time it's not at x. We're inputting a value of 3 altogether, which is why all the function evaluations that we see here are at 3. So we have the derivative of f at 3, we have the derivative of g at 3. And when you go to write this out, the thought is, well, that's just a quotient rule. So it looks like that. Whether you call this f at x or f at 3, that's the schematic for a quotient rule. So if we were to follow out that process, we would say f prime at 3 times g at 3 minus f at 3 times g prime at 3. So I copied essentially what's in the numerator by this red dot, but I plugged in at 3 because now we have a specific input. Then we divide by g at 3 squared. So now we need to do 5 function evaluations, not all different though. Looks like 4 different evaluations, 2 of them derivatives, and 3 of them ordinary function evaluations. So that's step 1 of the process. Essentially, you just write down the quotient rule and say the function at 3 for each function that occurs. The next step is tricky because we have to do a bit of bookkeeping and be very, very careful with what output we give to f prime at 3. F prime at 3 is not -4. We have to specifically take the derivative. F prime at 3 is 2. So that's just the new trick at this stage, making sure to grab the right output. So we throw an output 2 there and multiplies g at 3, seeing the row above, that's a 5. Then we go minus f at 3, that's a -4. Then it multiplies g prime at 3, but that one's the derivative, so go to the highlighted one, -4. Then in the denominator, we're squaring. It indicates g at 3, so just squaring a 5 altogether. let me put it in black to not miscommunicate. That one was not a derivative, just a function evaluation. So that's the next step in the process. Last step is just order of operations, essentially. Crank this out and get a number. But any questions at all, folks? Writing down the quotient rule or doing the evaluation to the right? Okay, well, as we fully simplify this, here's what we're going to get. Numerator is altogether 10 minus 16. Denominator is at 25. So it looks like negative 6 25ths altogether. Let me double check my arithmetic. Okay, that looks about right. Following order of operations. That 5 doesn't look like a 5, though. Let me correct that part there. So that's the name of the game for this one. And now we're just redoing it all over again, but this time using the product rule. Product rule looks a lot like what we have here, just the numerator portion though, and flip that sign to a positive. So it'll go f prime at 3, g at 3 plus f at 3, g prime at 3. So here's our big change, no denominator, a flipped sign. But aside from that, it's highly, highly similar. And the more you spot these kind of patterns, these kind of similarities, the easier it is on our brain to kind of internalize it, figure out what goes where, and get very fluent with both rules all at once. So now we're just about done. Just like before, we have to put in the right evaluations. First one's the derivative, so it gets a 2. Next one's a function value for g, so it gets a 5, plus function value for f, so that gets a negative 4. Almost feels like deja vu. These are pretty much the same things. Then g prime at 3 gets a negative 4. Now finally, order of operations on this will give us 10 plus 16 for a 26 altogether. So that's the full rundown for this kind of problem. And again, it's pretty odd. We don't know a lot about the functions, but it's all just forcing us to take a closer look at both quotient and product rule to see how things combine. Well, still one more problem we want to do on these notes, just for the sake of extra practice. We haven't done any problem where there's a higher order derivative on these notes. So that's what we'll do on the next question. But any last thoughts or comments at all, folks, with what we've done so far? Okay, well, let's turn to the last example of the notes. For example 4, we have two things we want to compute. It says compute y prime and y double prime for that function given there. Y equals 3 minus x squared times e to the x. So let's give this a try. If that's our function y, and we want to do y prime to start out, that one altogether is going to be the product rule we have to take. But if that's a product rule, there's two factors. The first factor here and the second factor. It's best to do it in this format. Distributing e to the x into the group, it's not going to eliminate the product rule. There'll still be a product rule when we have negative x squared times e to the x. So in my opinion, it's easier to do it just right in this format. So here's how it goes for y prime. And we mentioned each time we did the product rule and quotient rule, just for the sake of showing how it goes, we did the whole placeholder strategy each and every time. But there are other strategies and ways to do this. If you feel like you're getting a good handle on both the product rule and the quotient rules, here's another way to go. Let me know how you feel about this as a kind of a shortcut onto the method. When people do the product rule for this function, and they've done lots of product rules, say dozens, they did their homework, they've gone through the exam and so on, this is usually the way it's done on paper. They look at the first function, 3 minus x squared, and they just differentiate it right here, right now. The derivative of that is going to be 0 minus 2x. So there it is. That's the derivative of the first function. Then copy in the second function, e to the x. Go plus, copy in the first function, 3 minus x squared. And then instead of saying we're going to do e to the x prime, let's just differentiate it right here now. E to the x derivative is just e to the x. And again, that's how the product rule is typically done. Same for the quotient rule. Any questions seeing it done in this kind of way? Okay, well, if you like that shortcut, that's a shortcut you're always welcome to take on a homework assignment or an exam assignment. In fact, it's encouraged to see it this way because when you go to take Calculus 2, Calculus 3, and so on, other instructors start doing it in this way more often than not. But when you're starting out, just learning, doing your very first homework assignment with product rule, quotient rule, not a bad idea to go with the placeholder strategy first, just to see how everything connects. Now we have to go to the higher order derivative, the second derivative of y. So that means another product rule. So here's how this one is going to go. Y double prime. We're doing another product rule. First, there's going to be a product rule that occurs here, and another one that occurs here when we go to differentiate the prior function. Recall y double prime just means differentiate the last line, y prime itself. But again, there's two product rules to do, so let's see how these go. With that shortcut in mind, here's what it would look like. Well, there's a lot going on here. Let's maybe skip the shortcut on this one just to show what the schematic would look like for the product rule here. So let me just focus on these two. Let's take our time with this one and write it out this way. So that's the format for the product rule. I'm going to drop the color coding because I'm running out of color so far. So the product rule becomes all of this when we go to write it down. We take the first factor, negative 2x, second factor, e to the x, copy in that order for all placeholders. So negative 2x, e to the x as well. So that'll take care of the first product rule that occurs. And then when we go over here, that's just another product rule. However, let's look at that really, really carefully. When you look at 3 minus x squared e to the x, and you tell yourself we're about to differentiate that, that should feel like real deja vu because you have done that derivative already once. This is kind of weird, right? When we differentiated the function y and wrote it down carefully, the function y occurred inside the derivative of y prime itself. These weird kind of things can happen with functions. And so if we're differentiating that, we've already done it once before. There's no reason to reinvent the wheel. If this is y, the whole thing right here is y prime, so it copies in this way. Let's put in the notes, this is y, and so here is the result for y prime, plus a negative 2x, e to the x, plus 3 minus x squared, e to the x. This whole thing, this is y prime. So once we identified that we had the function y inside there, we just reused what we already had and dropped it inside. A very bizarre function when you really look at it in those kind of terms. Doesn't always happen, but this is like a mathematical miracle that occurred for this function. Any questions at all, folks, seeing that substitution occur? Okay, Well, let's simplify what we've got. Y double prime, now as we finalize these last derivatives, this one here is a derivative of -2, now times e to the x, and I'll drop the plus sign here and just say minus 2x times e to the x. Those are non-like terms, so we can leave them as is. Then minus 2x e to the x plus 3 minus x squared times e to the x. And lo and behold, we do have like terms here and here, so let's combine those. Y double prime is minus 2 e to the x minus 4x e to the x plus 3 minus x squared e to the x. We might be able to do a little bit more with this if we factored out e to the x, but no further terms look like they're really going to combine too much in a very big way. Maybe the constants -2 and 3. I would say this is a good stopping point for this kind of function here. What we did, folks, this is just our last topic, kind of a challenge one on getting the second derivative down using the product rule multiple times, but also identifying that that's the function y there. So just throwing in y prime here as a shortcut was a major step as well. And if you didn't see that identification and you just differentiate this again from scratch with product rule, no harm done. You're reinventing what you did before, but you'll still get the right answer. Well, that's the conclusion, getting through both the product rule and the quotient rule. What we're going to turn into next is a new class of functions, derivatives of the trigonometric functions themselves. But any last questions or thoughts before we take a look into the next section notes? Okay, let's close these out. We're not going to try to race through the next section, mostly get an early start on it so we're not too bogged down after exam 1 next week with all those sections there. And the first portion of the notes really is just a big algebra review altogether. In a calculus course, we're pretty much using everything you've done in pre-calculus 1, pre-calculus 2, looking at polynomial functions, exponential, logarithmic. Now we're turning into derivatives of trigonometric functions. We'll later on get into inverse functions, inverse of the trigonometric ones, and even look into a new class of functions you might not have seen before. But again, if it's been a while since you've done pre-calculus course, college algebra or trigonometry, it's sometimes called, this material here is going to be really, really helpful when we're going into section 3.3. We made a comment on week 1 of the course that there's actually a lot of trigonometry in calculus 1. There's plenty in calculus 2, probably even more in calculus 3. So trigonometry is one of those things that just never goes away. You start to use it more and more as you go. So if you feel like you need a refresher, this is a good set of notes for all the concepts, trigonometric identities. It's a great one-stop shop. And also in your very own textbook, if you turn back to the appendix, I forget which appendix, but one of those appendixes in the very back of the book is on trigonometry itself. It's a pretty nice short write-up that will refresh a lot of the things that you've done before in pre-calculus 2, studying trigonometry. So we'll refresh trigonometry as we go. We define trigonometry using the so-called unit circle. It's the circle centered at the origin with the radius 1. Its equation is x squared plus y squared equals 1. And it gives us this display we see here. The measurement that we're going to be using is typically not degrees, although there's sometimes exceptions. The default assumption is we're always working in radian measure. So instead of dealing with cosine of 60 degrees, we'll often say cosine at pi/3 instead. So that's the setup so far. Here's our diagram for the unit circle. If you feel a little bit rusty about these on exam 2, you could copy some of this information down on the notes that you're allowed to bring into the second exam. At any point on this unit circle, we do a rotation theta. In standard position means we measure theta rotating going in the counterclockwise direction. maybe we rotated somewhere from here to here, some random point. Arrow here says we rotated theta in that direction, so theta is a positive angle now if we rotate counterclockwise. And what we're fundamentally interested is in where this intersects the unit circle, x squared plus y squared is 1. There will be coordinates x, y here. And when we say the x coordinate, we mean cosine of that rotation theta. And when we say the y coordinate, we mean sine of that rotation theta. So that's our crash course, our fast primer revision on trigonometry. Once we have sine and cosine, there's 6 trigonometric functions altogether, but they're just rearrangements of both sine and cosine. Tangent is sine divided by cosine. And sure, you could say it's also y divided by x, but for our purposes in calculus, it's better to say what the function is. So I wrote it out in this way, sine divided by cosine. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. And cotangent is the reciprocal of tangent. So go from cosine to 1 over cosine, you have secant. Likewise, go from tangent to 1 over tangent. That's just flipping cosine and sine. So cotangent has cosine divided by sine altogether. Well, that's, again, a rough crash course on trigonometry. Any questions or comments at the moment? Okay. Well, aside from the fact that we have these trigonometric functions, what we really want to do in these notes is differentiate all of them. So we're going to look into 6 new derivatives. That's the namesake of this section, derivatives of trigonometric functions. And the book does a really good proof on what the derivative of sine should be, extending it to what the derivative of cosine should be. And actually, that's the hardest part about all of this, just getting started. I'll leave it up to your reading to show you how that goes so we don't take up too much time doing a derivation. But here's another graph that's being shown in the book as well that makes the results seem pretty plausible. Let's put down 2 functions. Y equals cosine. Let's actually start with sine of x. So we're thinking of this as now being an input, x radians, and this is the sine function coming through as a wave. Here's y equals cosine of x. And I want to kind of emphasize the y-axis a little bit more. So let's go from negative 1.1 to positive 1.1. I think that's a better picture for us. And finally, here is our major result. If we can make sense of that theorem down below, then the derivative of every other trigonometric function will follow from that one result. So let me scroll the diagram to about this spot right here. Maybe back a little bit, it's not a bad idea. Let's go to about here. Oops, there we go. So the theorem that the author takes some painstaking work to derive on the section 3.3 to start out is the derivative of sine turns out to be cosine. That's kind of unusual. And likewise, the derivative of cosine at x becomes negative sine at x. Let's emphasize this one right here and see if we can see what's going on with that by analyzing it through the graph. The same kind of graphical analysis will help us see why the second formula is also true. Well, I'll focus on this one here. So when we look at these 2 curves, the one in blue is the sine wave. The one, hang on, I got that backwards. The one in red, this one is the sine wave. A little arrow can't hurt. Let's put it here. Here's sine x, and the one in blue is the cosine wave. Here's cosine x. And now, if we think of cosine x as being equal to d by dx of sine x, the derivative of the sine function, what that means is we have the graph of the derivative for sine in blue. This should be the derivative. Let's think about how we plotted those derivatives in section 2.8. The first thing we looked for was the horizontal tangent lines. That's where the curve reaches a turning point, whether it's a local maximum, local minimum, or you could say absolute maximum, absolute minimum. The absolute maximum to the function is 1. The absolute minimum to the function is -1. But every one of those spots, the tangent line is completely flat, horizontal, which means the slope is 0. But anytime you say slope, you have to recall you mean derivative. If the slope is 0 right here, that means the derivative is 0 right here. But that's what the blue sine wave is saying. Derivative being 0 means it intersects on the x-axis right at that point. Likewise, we have intersection here, an intersection here, here, and here, one more. Let me get in a horizontal tangent line on this one, the one I forgot. Now going back to the red curve, every single spot where it reached a peak or a trough, horizontal tangent line in either case, you can go vertically up or vertically down, and notice the curve in blue, it always intercepts right at 0. That means it's got the right intercepts for sure. And now if you look at this piece of the curve on the side wave, it's always increasing until you get to here. That's where it turns around. But if it's always increasing on this branch up to this point, that means the derivative, which we're claiming is cosine, should always be positive. And it absolutely is. It only goes negative through here when the curve for sine is decreasing. So if sine is decreasing, the curve in blue is always below the x-axis. So let's draw maybe, oh geez, that was the wrong thing to click. Let's draw maybe one more thing so the diagram doesn't get too overwhelming. But the idea is from this domain, from here to here, sine x is decreasing. It's going down. But in that same domain, we have that also cosine x is less than 0 in that same exact domain. And that makes it plausible that it's really the derivative once again. Now, this isn't a proof, but it makes it highly plausible that once again, if you differentiate the sine curve, you really are getting the cosine curve. And the author makes that a 100% fact by giving the legitimate proof using the definition of the derivative. Well, that's one look at how this theorem works, why it's plausible. You can do the same thing with two new graphs on this one, cosine for one, negative sine for the other. But we'll leave it off on just the first look here. Any questions at all, folks, with the graphical analysis on checking that derivative? Okay, let me screenshot this in just in case you wanted to take another look at that at any point. We'll plug it in here. Looks like it barely fits. So with all that information on the table, we now have a new class of functions, 6 trigonometric functions altogether, and we start off with 2 given derivatives. These have been proven rigorously through the textbook, so we can now take these for granted. The derivative of sine is cosine, and curiously, the derivative of cosine is negative sine. Now we need to differentiate 4 more functions and find their formulas, but we'll prove one of them. Let's do the one for cosecant. My claim is that the derivative of cosecant is negative cosecant theta times cotangent theta. Well, to prove that, again, we have to be fluent on this part right here, the trigonometry portion. We have to assume this knowledge. If this stuff comes up in an exam situation, you must know that cosecant is 1 over sine, secant is 1 over cosine, and so on. So we will be reviewing this as we go. And this is fair game to put on your notes once again on exam 2 if you feel a little bit rusty on trigonometry. So to do this kind of proof, the first thing we can do is, I'll write out this way, cosecant theta I'm converting the formula written as d by d theta, the traditional way the textbook writes it, into prime notation. That's a fair way to say it. Now we can say, for differentiating that, we have really 1 over sine theta. That's the thing we're really differentiating. And we mentioned before, when we were looking into the quotient rule, usually we would not use the quotient rule in this situation when there's a constant in the numerator. But for this problem, we kind of need to. We actually need the quotient rule because it's not just a variable x, like we saw in the prior section notes. It's a whole function of a variable theta. And sure, you could rewrite 1 over sine theta as sine theta to the power of -1. This is not sine inverse theta. This is an exponent, -1. But if you were to differentiate this, this requires the chain rule. But that's in section 3.4. We've never even mentioned the chain rule before. So that's an even trickier derivative. So for that reason, even though there's a constant in the numerator, this one and only time probably in the whole course, we will use the quotient rule here, just so that we don't have to reach for a rule we've never studied before. But that's just as well. We get to practice the quotient rule on this one. So I'll put here, use quotient rule. So if we're using the quotient rule on that thing, we can now say that the derivative of cosecant theta is, it's organized as before. We have a constant function for the numerator, the sine theta function for the denominator. Let's go with placeholders on this one. We'll put a derivative here, copy a function, go minus for quotient rule, copy a function, put a derivative here, and then square a function in the denominator. So as written out, that's the entire quotient rule setup. Now we just plug in the functions. Let me finish off the highlighting though. I think we usually did it this way in the last section notes. So the functions go 1 sine theta for top function, bottom function. So we copy them in left and right, left to right. 1 sine theta. Then recall for the denominator, we just match the denominator in the original problem, which is sine theta. So sine theta goes down below here. So that's our setup to get started. And now we're kind of on our way. Nice for this is, we know the derivative of sine theta, it's right here. Derivative of sine theta is cosine theta, so we can put in that result there. This is the derivative of a constant, so it just goes to 0. And so that's going to make this whole thing simplify a whole lot. Cosecant theta is now going to be equal to, when we write this out, 0 from the derivative over here, multiplying sine theta. So it's going to kill off that sine theta. -1, or -1 times sine theta is going to be minus. I said that in a weird way. I'm just going to drop the 1 here, put in the derivative of sine theta, which is cosine theta. So the better way to send that is -1 times the derivative of sine theta is just negative cosine theta, using our derivative result here. We're just copying in that extra negative sign. And for the denominator, you might recall that there's some nice ways to write out sine cubed, sine squared, cosine power 4. The shorthand for a sine theta function squared is sine squared theta. And we use that shorthand from pre-calculus all of the time in a calculus setting as well. So here's where it lands after we take all the derivatives through the quotient rule. Now we must simplify a result. We get 0 here, so we can drop the entire term and write this as negative cosine theta divided by sine squared theta. That looks problematic, right? Negative cosine theta over sine squared theta, because our goal was to prove that if you differentiate cosecant, you get negative cosecant theta times cotangent theta. That looks different, right? But then we have to ask ourselves, is it really different? This is why when you took a pre-calculus 2 class for trigonometry, you might have been felt it was kind of weird and challenging even when you had to do simplifying trigonometric expressions, proving trigonometric identities. There's a lot of work like that that comes up in a trigonometry course, and this is one of those purposes. We need to prove that negative cosine theta divided by sine squared theta is equal to that. It's a bona fide trigonometric identity, and we'll do it just by simplifying this down. So new line, cosecant theta prime, the derivative of cosecant theta is all of this. But here's a great strategy when you're trying to prove an identity. We're trying to prove that we can get to equality on this thing. We already have the negative sign, so we're good to go on our negative sign. That's nice. Let's copy it in. We need a cosecant, but recall cosecant is just 1 over sine. And if it's sine squared here, we can split off a factor. It's really a sine times sine theta in the denominator. Dividing by sine theta is the same as multiplying by 1 over sine theta. So you can just split one off just like that. This is the same expression because sine times sine gives you back sine squared. Nothing else is different about this. But cosine divided by sine is in fact cotangent. 1 over sine is cosecant, and we have our required negative sign. So this is now equal to negative. Cosecant is the simplified function for the reciprocal of sine. So cosecant theta here. Cosine theta divided by sine theta, we simplify to cotangent theta. So that proves the underlying result. Derivative of cosecant theta, it's kind of weird. It's a negative sign. Cosecant shows up again, and then we just multiply by cotangent theta. Well, any last questions or thoughts at all, folks, getting to this stage here? Okay, well, we have the derivative of sine is cosine, the derivative of cosine is negative sine, and now we have that the derivative of cosecant is negative cosecant times cotangent, so just 3 more functions to go. But deriving the derivative for all of those other functions, it's the same exact story as this one. So you can try that out as kind of a challenge problem. But let's scroll down to the full set of results. The namesake of this is derivatives of trigonometric functions for section 3.3. And here they all are. Here are the derivatives of trigonometric functions. So we have derivative of sine is cosine, derivative of cosine is negative sine. Here's the one we derived for cosecant. It's negative cosecant times cotangent. Derivative of tangent becomes secant squared at x. Derivative of secant is a secant x tangent x. And derivative of cotangent becomes a negative cosecant squared at x. So that's our entire list of derivatives of trigonometric functions. Well, I put here in the highlighted yellow just to emphasize it. These results get used all of the time. In a Calculus 1, Calculus 2, Calculus 3 setting, once you're in Calculus 2 and Calculus 3, it's assumed that you just know these. And if you're taking, say, some random calculus instructor for Calculus 2, Calculus 3, if you happen to forget one of these, this could be really harmful in an exam setting. They're not necessarily going to give you this information in an exam situation. These are things that are used so routinely that if you're, say, in a differential equations class, an engineering course, a chemistry course, any course that uses calculus, and Calculus 1 was a prerequisite, this is something that's assumed to just be known. So even though you can put this on a page of notes, for example, for exam number 2, when you take the second exam, my encouragement to you is definitely memorize those. You don't want to look up a derivative when one of these come up, and they come up a lot in your journey through calculus. Because they're so important, here's a decent strategy to think about how to memorize these. There's some decent patterns here you can take a look into to help out your mind absorb the information. I would start by taking a look at what happens when you differentiate a co-function? For example, if you differentiate cosine, you get a negative sign that comes up. That's not a coincidence. If you differentiate a cosecant function, negative sign occurs right here. And if you differentiate a cotangent function, negative sign occurs right here. And that's a pretty helpful pattern. That nails down where the negatives and positives are, although their derivatives have a positive leading coefficient. So that's a great pattern to think about. Next one to think about is how if you have, say, the derivative of secant down, derivative of secant is just secant times tangent. That's a one that I would definitely memorize, get it down pat, because there's a great trick if you change from secant to a cofunction. Go from secant to cosecant, all you're changing is the sign becomes negative, but then secant becomes cosecant here, and tangent becomes the cofunction, cotangent here. That is a really awesome pattern. You go from a function to a cofunction by changing the sign and changing all the functions to their cofunction, secant to cosecant, and both spots here and here, tangent to cotangent. That really helps your brain internalize this information. So memorize these two right here, get secant down pat, know the trick to get cosecant. And same idea with tangent. This is one you want to just have right burned into your brain, in the back of your mind, always ready to go. Derivative of tangent is secant. But then if you go from tangent to a cofunction, notice, go tangent to cofunction. Because you're differentiating a cofunction, you put in a negative sign. But you just take what you've memorized, secant squared, and go to the cosecant squared. So there's another relationship between the function and its cofunction, and that derivative. So there's a lot of patterns to take a look into, so it doesn't get too busy. Just highlight the negative sign pattern. That's a fundamental one. There's probably other patterns that you've noticed here that just hasn't ever occurred to me. So anything that you can spot that helps your brain internalize that information will be very, very useful down the line through this course and any other course that uses it as a prerequisite. So that's the full list of derivatives of trigonometric functions. What we'll do on example 2 is practice taking them. We'll do maybe 1, possibly 2 today, and then come back on Tuesday, refresh on this table here, and just take more and more derivatives to finish out the notes. But any questions or comments at all, folks, before we try out an example? Okay, well, let's give this a try. Example 2 says, compute the derivatives. F of x is 2 cosecant plus secant. But really, it's not too bad. Really, we're just using the foregone information right here. You don't have to derive any of these. These are now formulas we can take for granted. So now we can say f prime at x is going to be, starting out with the constant multiple rule, 2 stays where it is because it's multiplying a function. We're multiplying by cosecant. That means you're going to get a negative sign. And derivative of cosecant is itself cosecant x times cotangent x. So that's the formula we used here up above. Now we're using the sum rule. We're just differentiating term by term. Take the derivative of secant. It's not a cofunction, so we don't put in a negative sign. And it goes kind of the same way as derivative of cosecant, other than the negative. Derivative of secant is itself to start. Then we multiply it by tangent x. So that's this row right here, second column on the derivative of trigonometric functions. And I would say that is a fully simplified form. You absolutely need these parentheses here because it's not 2 minus cosecant x cotangent x. It's 2 times negative cosecant x cotangent x. For me personally, I would take the extra step just for clarification and rewrite it as -2 cosecant x cotangent x plus secant x tangent x. To me, it just looks better that way. And you avoid unfortunate miscommunication where if you did drop parentheses, this could lose a point because that's a whole different function. That wouldn't be correct as written. So either leave it at that stage, definitely with parentheses, or just make it blatantly -2 times in that format there. Well, that's one done. They again go pretty fast. Let's maybe give one more a try and then take final questions and call it evening after this G a T function. Any questions or comments first before we try for one more? Okay, let's give this one a try. First thing to note is this one is a product rule problem out of nowhere. And that's what's going to happen with the next of the problems down the line. We're using all the formulas we've been using from 3.1, 3.2, including product rule and quotient rule. So if you have two functions being multiplied, product rule is an important one to run through to simplify this. But at the same stage, the cube root of t is just not a nice format for differentiating in the first place. So it's a good idea to just rewrite this into a better format. Rewrite it as t to a power 1/3 times sine t. Reason for doing that is we want to use the power rule on this. So we shouldn't have it in radical notation, cube root. We should exhibit the actual power if we're going to use the power rule. Now here's the process for product rule, our next step. Doesn't hurt to emphasize that's what we're about to use next for the sake of the notes. The derivative of g at t, or g prime at t, here's the process for product rule. We differentiate that function first, right where the red dot is. Taking the derivative of that function, I guess you could say derivating that function, but that just sounds weird. Taking its derivative, you get 1/3 times t to the power of 1 less. 1/3 minus 1 is just 1/3 minus 3/3 for a power -2/3. Then the rest of the process is we copy the second function, sine t. We go plus with the product rule, copy the first function, t to the power of 1/3. And then finally, multiply by the derivative of the second function, sine t. We have that up above, derivative of sine is cosine. So this will become cosine t. So really all we used when we evaluate it by the product rule is that fg prime is f prime times g plus f times g prime. This time we did it all in one line. We did the f prime right away. That's the portion in blue. We did the g prime right away. That's the portion in green. And that's the whole punchline to this one. Not much more to do. There's no purpose to try to simplify by doing anything with factoring. And so this is a great form to just leave it in right at that step. Well, again, these rules above are extremely fundamental to any class that uses Calculus 1 as a prerequisite. If you're a fan of flashcards, these might be good ones to write down. Good strategy also is anytime you start a homework assignment, for something critical like this, it might not be a bad idea to just grab a fresh piece of paper, list sine x prime, cosine x prime, tangent x prime, same for the right-hand column, and just fill them all in. Test your knowledge. Do that as a drill a few times, and it's just going to snake its way into your brain. You might dream about it after a few times. So the more you practice writing these down, memorizing them, the more you use them, and try to memorize them from scratch without just looking them up from a table each time, the more you'll get them memorized. But I think this is probably a good stopping point for us. Next question is not too bad, but we need other tricks to help us out with that one. Some trigonometric identities. So we'll review some more trigonometry after the exam on Tuesday. But any last questions or comments at all, folks, before we call it a night today? Okay. Well, once again, we'll have our second exam on Monday, so we won't hold class officially on that Monday's class. That's the wrong thing to pull up. But if you're working on studying on this exam, maybe you're getting caught up on late work, that'd be a great strategy to start off first. Or if you just have any questions on the problems here or any generic questions whatsoever, don't hesitate to email. I'll be checking my email Friday morning, Saturday morning, Sunday morning, and I'll be checking it extensively Monday as well. I'll be happy to connect with you and get back to any questions you might have. But have a great weekend, folks. Try not to work too hard. We'll be back together as a class coming back on Tuesday, working through the rest of these notes here and then into the chain rule, the next section. But have a great weekend, folks. I'll see you all on the start of next week.